All right, so welcome everyone once again to the point distribution webinar. This will be the last talk for the summer session. There will be an email sent out soon announcing our continuation into the fall, as well as a call for speakers if anyone's interested for giving talks in the fall. We'll be starting back up on September 16th, so giving about a 2-week break between now and when we start up in the fall. But yeah, so for our final speaker for this summer, we have David Krieg from the Johann Kepler University at Linz, talking about order optimal point configurations for function approximation.
Yes, thank you, Ryan. And I'd like to thank all 3 of you guys again for organizing this kind of nice seminar, which is particularly nice in these times when conferences don't work so well. And so as Ryan already told you, I'm going to talk about good point configurations for function approximation. And this is joint work with Matthias Sonnleitner, who also already has given a talk in the seminar about isotropic discrepancy. And I guess that many of you are not really familiar with the concepts of information-based complexity which are behind these this work. So I'll start with some introduction on that. So what kind of problem do we consider? We assume that we have some bounded and convex domain omega, d-dimensional. For this slide, the convexity and boundedness is not necessary, but it will be important on the following slides. So I already fixed the domain omega, it's bounded and convex. And we consider some function space, capital F, some normed space of bounded functions on this domain. And B of F shall be the unit ball of the space. And we have given some finite point set in the domain. And the points we call the sampling points. And now we want to approximate a function, an unknown function from the space based on the knowledge of the function values at these points. So what kind of algorithms are allowed? The algorithm looks like this here. It's just you take the function values and then some arbitrary map which maps the function values back to the space of bounded function, let's say. Okay, so in general, we admit arbitrary algorithms, but sometimes it's preferable to only consider linear algorithms, so linear mappings phi, in which case I use this pink color to distinguish. Okay, now these are the algorithms, and the goal is to approximate a function, and the error we will measure it in the LQ norm for some arbitrary Q. And now the minimal worst case error that can be achieved with the given sampling points is defined like this. So the worst case error of the algorithm is the supremum part. So we take the difference of the function and the output of the algorithm in LQ. And it's called worst case error because we take the supremum over all functions from the unit ball of the space. And minimal worst case error because we now optimize over all algorithms that use the given sampling points. Yes, and this lin here means that we only optimize over all algorithms that are linear. So you can, for the whole talk, you can think of the linear algorithms or without. So this pink thing is always optional.
Sorry,
Okay.
if I can quickly ask, just to make sure I understand the terminology. When you're saying algorithms, so the algorithms are maps from a function to a function, right?
Yes.
Okay, thank you.
Yeah, so the algorithm goes from the function space F to the space of bounded functions L infinity. Yeah. And it's of this form that it's first you take the mapping which computes the function values, and then you take some arbitrary mapping which goes back from Rn to the L infinity. So these are the allowed algorithms. And now this quantity down here measures somehow the quality of the point set for the problem of LQ approximation on the function space F. The best you can do with the sampling points that you have. Okay, and what kind of function space do we consider? We consider Sobolev spaces. So in case you don't know them, let me shortly explain. The Sobolev space of smoothness S, so S is the smoothness and B is the integrability, is defined like this. You take all functions from LP whose derivatives, or let's say weak derivatives, up to order S are again LP functions. And this is a Banach space if you equip it with this norm, for example. So you take the LP norm of the function plus the LP norm of the derivatives. Yeah, and here the LP norm of the derivatives, I take again a little LP average over all derivatives of order S. But of course, you can exchange this P in little LP for some arbitrary other index, and you will get an equivalent norm because this little LP is on some finite index set. And in case you don't know what weak derivatives are, that's not important. You can also just think of the Sobolev space as the space of functions for which this derivative here is in a classical way defined, and then so the space of S times continuously differentiable functions, for example, and then equip it with this norm. In this case, it won't be a complete space, but it's not important for the results which I write down. Okay, and we will always assume that the smoothness S is greater than the dimension divided by the integrability, because this ensures by the Sobolev embedding theorem that the functions in space are indeed functions, not equivalence classes with respect to the Lebesgue measure, and they are even continuous and bounded functions. So if anybody wants to follow Ryan and ask a question in between, you are welcome to do so. Okay, so now we consider the problem of LQ approximation on these Sobolev spaces. And of course, we are not the first to study this problem, but usually people ask, how good are optimal sampling points? So we take this error of the point set, and now we also minimize it over all point sets of cardinality at most n. So this is called the nth minimal worst case error for obvious reasons. And a result by Erich Nowak and Hans Triebel from 2006 tells us that this nth minimal worst case error is of order n to the minus s over d plus, and then some correction term 1 over p minus 1 over q plus, where the plus means that I take the maximum of this expression, and 0. Yes. And if you look at the paper of these authors, then you see even more. You see that they also prove that the optimal order is achieved for point sets with covering radius of order n to the minus 1 of d. So what's the covering radius? The covering radius is the largest distance of a point in omega to the point set p. So you can also view it as the radius of the largest empty ball amidst the point set. Yes, and this cannot be smaller than n to the -1/d. And we already know from this paper that if it's of order n to the -1/d, then the point set actually achieves this bound. Yes, and just a remark, Novak and Treble, they proved the result for a little more general domains than those which we consider here. They consider bounded Lipschitz domains. Yeah. And convexity implies that the domain is a Lipschitz domain. And we only consider the convex domains. And the proof is actually based on a result of Holger Wendland from 2001, I think. I don't see it with you guys in the picture. Yes, 2001. And this one is important for us too. We will use it in the proof. And actually the result is much older if you consider special domains like the unit cube, for example. Okay, so now what's our goal? What are we interested in? So this is for optimal point sets, but you can probably imagine that in many applications, you cannot choose the sampling points at your own convenience. And so we ask, if we have an arbitrary point set, can we somehow, is there a simple way to determine the quality of the point set, to determine this minimal worst case error, which I wrote down in the beginning? Yeah, or a similar question, can we somehow characterize those point sets or sequences of point sets that achieve the optimal order of convergence? And in particular, we are interested in random sampling points, so points which are distributed independently and uniformly on the domain. So this was actually our initial interest in the problem. We wanted to find out how good these kind of point sets are, because you can imagine that's maybe a good model for reality, that you just get random data at points. And we want to know how good these are. Yeah, and a short remark here. It's actually quite common for sampling-based algorithms that authors use the covering radius of the point set to determine the error of the algorithm. So similar to the slide before. But somehow this does seem a little too strong, a little too restrictive, because maybe you can imagine if we want to approximate the function in LQ for some small q, so maybe in L1 or something, then it should be okay if in the point sets there are few gaps which are larger than n to the -1/d, as long as most of the gaps are small. Because if there is a larger gap at some point, then this should somehow mean that in this area you maybe make a little larger error, but as you average over the whole domain in L1, then this should not be so important that you make this error in the small area. And it's easy for me to say this because we proved something like that. So here's our main result, which goes like this. So we have two cases. In the case that Q is larger than P, so recall we do LQ approximation in the Sobolev space with integrability P, then the mainstream actually is already right. So the quality of these point sets, no matter whether you consider linear algorithms or arbitrary algorithms, is determined by the covering radius. So the L infinity norm of this distance functions is nothing else than the covering radius. And well, it's precisely given by the covering radius to some power. But in the case that the integrability in the target space LQ is smaller than P, then actually the covering radius can be replaced by the L gamma norm of the distance function, where gamma looks like this. So it's S times the inverse of 1 over Q minus 1 over P. So the larger the distance between Q and P, the less restrictive is the condition on the point set. So only the L gamma norm has to be of the optimal order to achieve the optimal order for the LQ approximation problem. Yeah. Yes, that's the result. And so what are we going to do now? Before I come to further discussions, I want to show you, I want to sketch you the proof. I want to show you some ideas, and it's clear that you won't understand everything. It's not made for that. It's just, I want to give you an impression. So if you understand everything, then I can be really proud of myself, but I guess it's okay if you just get some impression. So after the proof, everybody can wake up again, and I will talk about some related results, also including the integration problem, which is quite close to the L1 approximation problem. And in the end, I will give some examples and also talk about a few open problems. Okay, if there are no questions so far, then let's start with the proof. So I won't show you the proof for everything. First of all, I will only talk about the case that Q is smaller than P, but that's not really a restriction, because this case is harder and it's more interesting. Case Q larger than P was basically known before. And I will also only talk about the error of arbitrary algorithms, not necessarily linear algorithms, because then the proof looks a little easier. And I will do a third restriction. I will consider a little smaller space. I will only consider the Sobolev space of those functions which vanish on the boundary of the domain. So you can consider this space as the space of functions, of Sobolev functions on the whole RD, whose support is contained in the closure of omega. In other words, this means that I have the additional assumption that the function and all derivatives which exist in the classical sense vanish on the boundary. Okay. And so how goes the proof? The first ingredient is a result from information-based complexity, which is quite general, and it goes like this. If you have a normed space F, like in the beginning of bounded functions on omega, in this case, the Sobolev space, we can define the radius of information. That's how it calls. And it's just the supremum, the largest LQ norm of a function, which is in the unit ball of the space and which vanishes on the point set P. This is the radius of the point set P, the information given by the sampling points. And the lemma which we need is that basically the error, the minimal worst case error for arbitrary algorithms is basically the same as this radius of information. And well, I say here the author is folklore, but you can find the result in the book of Nowak and Wozniakowski. Yes. And you even have equality here, that the minimal worst case error is exactly the same as this radius of information. One such case is if F is a Hilbert space. And then we also have the equality for the linear algorithms. But in our case, we do not always have this equality, at least to my knowledge. Yes, and because I like this really much, and because I want to advertise information-based complexity, I want to show you the proof of this result. So how does it work? The lower bound goes like this. So the lower bound for the error. We take some function f star in the unit ball of the space, which vanishes on the point set. So of the range of the supremum. And now if we have any algorithm of the form from the beginning, so any algorithm which is a composition of the function evaluations at the point set and a function phi, which maps from the data back to the space of L infinity functions on omega. Then for any such algorithms, you have that the output of f star and minus f star is the same because the function values are 0 in both cases. So no algorithm which only uses the information at the sampling points can distinguish between f star and minus f star. Must be the same output. That's why we call such functions f star also fooling functions, because it fools the algorithm. And what does that mean? So the worst case error of the algorithm, it was defined like this: the supremum of distances of the output of the algorithm and the function in LQ. This is of course larger if I only take the supremum over the two elements f star and minus f star, which are both in the unit ball of the function space. So here I just restrict the domain of the supremum. And because the output is the same, I can write SP of f star in both cases. And now triangle inequality immediately gives me that this maximum must be larger than the LQ norm of f star. So to put it a little differently, the best we can do, the best the algorithm can do is to put, to choose the output right in the middle of f star and minus f star, and this would be the 0 function, and then we would have this error here. And this means that any algorithm has a worst case error, at least like this, and then taking the supremum, we get the lower bound of the result. And for the upper bound, now we have to consider a particular algorithm and show that the error is smaller than 2 times this radius of information. And what kind of algorithms do we consider? We consider any algorithm which is interpolatory. And what does that mean? We map a function from the unit ball of f to any function from the unit ball which interpolates the data. So which restricted to p gives the same as f restricted to p, yes? And then the output, of course, can be determined only by the knowledge of the function values at the points at f. So you can write it actually in this form. I didn't define phi, but it's possible to write it like this. And if you have an algorithm like this, then we consider the worst case error of this algorithm. And it's, of course, since SP of f is also an element of the unit ball with the same data, it must be smaller than supremum taking over all functions f and g, which have the same data, and then the distance in the LQ norm. Okay, but now if we consider the function f minus g divided by 2, then this is again in the unit ball. That's the triangle inequality, or the convexity of the unit ball. And so we get a function h, which is in the unit ball, and this function h actually vanishes on the point set because the function values of f and g are the same. So f minus g half is in the unit ball and vanishes at the point set. So this supremum must be smaller than the supremum taking over such functions, and here we have 2h. H is f minus g half, so f minus g is 2h. And if we now take the 2 outside, then we have exactly 2 times the radius of information as defined above. Okay, so this proves the result that the minimal worst case error is actually the same as this radius of information up to a factor of at most 2. Good. And now here's a second result which we use, which I think is somehow intuitive, but it's not so easy to prove. And it goes like this. So imagine this is the unit cube, the big cube is the unit cube. And given the smoothness S and the parameters P and the dimension D, then there are constants M and C, depending on these other parameters, such that if the function has a 0 in every one of these M to the D subcubes, so all of the same size, then we have this inequality. Then the supremum of the function is bounded by a constant times the semi-norm in the Sobolev space. So remember, this was the somehow the sum of all LP norms of the derivatives of order S. Yeah, so we can paraphrase this result as small derivatives and enough zeros yield small functions. Yeah, and enough zeros means also that the zeros have to be evenly spread in a certain way. Yes, and how do we prove this result? It follows from a result of Holger Wendland, which I talked about earlier, from 2001 on polynomial reproducing maps, and results on best polynomial approximation on the Sobolev space on the unit cube, which you can find, for example, in the book of Marcia from 85. So how do we use this result? First, recall, if we want to prove the upper bound for the error, we have to consider functions which vanish on the point set and ask how large is the LQ norm of these functions. Okay, so what do we do? For a given point x in the points in the domain omega, not in the point set necessarily, we consider such radii rho for which we have the following property. If we take the cube of radius rho, then in every of these m to the d subcubes, which are contained completely in omega, we have a point of our given point set P. Yeah, we consider all such rho, and then we take the infimum over all these radii. And we get something which we call a good cube. Yeah, so we take the cube around the given point x, which we call q of x, which has the smallest possible radius, such that in every one of these subcubes is a point of the point set, or a point which lies outside the domain. Why is that? Because we consider functions from these space which vanish outside omega. So on these cubes which go to the outside of omega, we automatically have zeros of the functions. And at these blue points, we also have zeros. So for these cubes, we can apply the lemma from before. I didn't call it a lemma, but the principle that enough zeros and small derivatives yield a small function. Yes, and I now do that, and the result is this. How do we get it? Well, we just scale everything to the unit cube and then scale back. And then we get exactly this behavior, the dependence on the radius of the cube. The computations are boring, which is why I don't do it. It's just transforming everything to the unit cube. So every function from this space, which finishes on the point set, satisfies this bound of the LQ norm on these good cubes for every x in the point set. Yes. And there's also a second property which we are going to use of the cube. So the R was the smallest possible value of such cubes. So if we take maybe half the radius, this means that one of the cubes is empty of P. So if we consider the cubes of half the radius, which I denote by Q of x half, the center should be the same. Then we have one of these cubes which is empty and contained in omega. Yeah, so it does not contain a point set outside, a point outside omega, and it does not contain a point of the point set. We are going to use that for the lower bound. Okay. And what are we doing now? Now we have for every point in the domain, we have a small cube around it where we can apply this lemma on the size of the function. And now the lemma, which is here, states that we can find a collection of such cubes that cover the domain in an efficient way. So we can find a collection of centers, yi, I call them, such that the good cubes, qi, they cover the domain or the closure of the domain, but they cover it in a way that every point of the domain or even every point of RD is contained at most a constant number of these cubes. In this case, the constant is 2 to the d. Actually, this point is the reason why I take cubes. I could have also taken balls or anything else. But for the cubes, it's a little easier to work with this third property of the efficiency of the covering. And I have a third property, which looks like this. These cubes, these smaller cubes inside the larger cubes, which I talked about, which are empty of the point set, they are actually pairwise disjoint. And maybe this kind of lemma reminds you of Vitali's covering lemma. And if you know it, and it's actually similar, but Vitali's covering lemma, at least the usual way it's written down, doesn't give you this. So we have to actually prove this. And so how do we start a proof? Well, this function R, which gives you the radius of the good cube around X, is upper semi-continuous. Yes, because if you move the center a little and you make, then you still have the cube of the same size is still good because the points were inside the open subcubes. And if you move now the center a little, then it's still a good point set. So R is upper semi-continuous. So we can choose Y1 as a maximizer of R on the domain, and then recursively YK as a maximizer of R on the domain, which is not already covered. And for these collections of Ys, we can actually prove these properties, but I don't do that now. I think it's for some calculus course exercise. So you can do that if you like, or you wait for the paper. Okay, now how do we put things together? So for the upper bound, we know from the IBC lemma, information-based complexity, on the radius of information, we have to consider an arbitrary function from the unit ball of the Sobolev space, which vanishes on the point set, and we have to bound the LQ norm of this function from above. And then we get bound for the minimal worst case error. So we take such a function, and of course the norm, the LQ norm to the qth power, is smaller than the sum of the LQ norms on this cube qi of the efficient covering, because it's a covering. Yeah. If we add these up, then we get every point of the domain, so it's an upper bound. And here now we insert the bound from lemma 2, I guess, which tells us how large the function can be at most. And the Ri is, of course, the radius of the cube qi. And now we get this. Okay, and then we do some Hölder inequality magic. And how do we do it? We do Hölder in the way that the q in the exponent of the Sobolev seminorm gets a p. And this has the advantage that here actually you only have an integral and not an integral to some power. Yeah, so the pth power of the Sobolev seminorm is just given by the integral of the pth power of the derivatives of order alpha, which I shortly denote here like this. Of course, you have to add up all derivatives of order alpha, but that doesn't change anything in the proof. Okay, and now you have this thing here, and these integrals, we can add up them easily. Why is that? Because this covering is efficient. So every y is hit at most a constant number of times. So this thing is actually bounded by the, if we take the sum, it's bounded by the integral over the whole domain. And the integral over the whole domain is bounded by 1 because we are in the unit ball of the space. So times the constant 2 to the d from the efficiency of the covering. But we are not interested in constants, at least not in this talk. And the Hölder inequality, the second part of the Hölder inequality now gives you a sum of the radio to the power gamma plus d. Gamma, by the way, is the gamma from the theorem. So it's s times the inverse of 1 over q minus 1 over p. And well, that's then actually the upper bound. And you can write this a little differently. The radius of the cube is actually the same as the distance functions to the power of gamma integrated over these empty cubes, qi star, because in these empty cubes, the distance is of the same order as the radius of the whole cube up to a constant. So in these empty cubes, the distance always is bounded below by a constant times the radius of the cube. And so this behaves like the integral of the distance functions to the power gamma over these small empty cubes. And since they are all disjoint, if we add them up, we are still smaller than the integral over the whole domain. And this is what remains. Yeah? And if you now consider what we get, then that's actually what we wanted to prove. Yeah, we have the gamma norm of the distance functions to the power of s. The q vanishes because I have this q here in the beginning. By the way, I hope you see my cursor. If you don't, then please interrupt.
We see it.
Okay, good. Thanks. Yeah. Yes, and that's actually the proof of the upper bound. We have the desired upper bound for all functions which are from the unit ball and vanish on the point set. And so we get a theorem for this restricted space. And how does the lower bound work? For the lower bound, we have to construct a Fooling function. Sorry to ask again, but do I have 50 minutes or does the 50 minutes already include the questions?
The 50 minutes don't include time for questions. So you get 50 minutes for your talk alone. Then there's time for questions afterwards.
Okay, then I don't need to hurry, thanks. Okay, for the lower bound, we use again these cubes which are empty of P. And what do? We take some smooth and non-negative function with support in the cube -1, 1 to the D, which are larger than 0 at some point, so some kind of bump function. And we scale it to these small empty cubes. And then we add these functions up with some height alpha I. Yeah, what we get is a function which has many small bumps. And this function, this actually vanishes on the point set because the qi star do not contain points of P. Yeah, the bumps are inside the cube's qi star. And I normalize it in the Sobolev space so that this F star is actually in the unit ball of the space and it vanishes on P. So it's what I called a fooling function before. And so the LQ norm of the function is a lower bound for the minimal worst case error. And now if I optimize the values of the alpha I, which I don't do here, so the heights of the bumps, then I actually get the desired lower bound. Yeah, so the optimal alpha I will be like the radius of the cube to some power. Yes, and that's actually the full proof. So in case you went to sleep while I talked about the proof, you can come back now. So here's the theorem again. And yeah, it's exactly the same as before. So the error is given by the L gamma norm. Oh, this person has weight of the distance functions to some power s, where gamma is infinity in case of q greater than b, and gamma is smaller than infinity in case q is smaller than p. And actually, you may generalize this result a little. First of all, I considered integer smoothness, but you can do the same for fractional smoothness. I don't know if you know Sobolev spaces of fractional smoothness, but they don't give any further problem. And what can you do? You can also generalize it to P and Q smaller than 1, so where you only have quasi-norms. And you can even generalize it to the whole range of so-called Triebel-Lysorkin spaces. And you exactly get the same result. So just for the expert Triebel-Lysorkin spaces, in this case, the result does not depend on the prime index of the space.
Something went very wrong with the audio.
Okay, is it still there, or do I have to do something about it?
It just went away. Try saying something again.
Do you hear me now? Is it everything fine?
Yeah, everything's fine now. Thank you.
Okay. Thanks. Okay, so it can be generalized to Triebel-Lysorkin spaces, and actually it can also be generalized to more general domains. So recall we considered convex bounded domains. And actually we need two things of the domain. The first thing is that we can, that there is a bounded extension operator from the Sobolev space on the domain omega to the Sobolev space on the RD. That's the first property which we need. This is, for example, also given for bounded Lipschitz domain. And the second property which we need in the proof for the space of functions which do not have to vanish on the boundary, we didn't use it in this proof, is that the intersection of these good cubes and the domain satisfies some interior cone condition. So if we consider the intersection of the cube and the domain, then every point in the set, for every point there has to be a small cone with vertex in the point that is still contained in the domain, and the radius has to be at least proportional to the radius of the cube. That's what we need. And this is where we use the convexity. This is one way to ensure this property. But there are other ways. Okay. And I promised you to say something about the integration problem. So the integration problem, in this case, the minimal worst case error can be defined similarly. So if we have a given set of sampling points, then the minimal worst case error is given by, well, the worst case error of an algorithm is given like this. We now take only the distance of the integral of the function and the output of some algorithm. So this is some curvature rule. And we take the worst case over the unit ball of the domain. Yeah, so you may also view this as the operator norm of the integral operator minus this linear sampling operator and of this functional. And you take the infimum over all algorithms, in this case, only the linear algorithms. Why is that? I could also admit nonlinear algorithms where I again map the function values via some mapping phi to this time the reals. But there's a classical result by Smolyak and Bakhvalov, which says that linear algorithms are as good as nonlinear algorithms in this case. So the infimum is the same if I minimize over all algorithms or only these curvature rules of this form. Okay, and actually for these bases, we have the same result as for L1 approximation. So the error, the minimal worst case error for the given point set is given by the L gamma norm of the distance functions to the power of S up to constants. And gamma is the same as for L1 approximation. So integration is as hard as L1 approximation. And let's play around a little with these results in the end. First of all, we can characterize optimal point sets. So if we have a sequence of point sets, then we get the optimal order of convergence if and only if this gamma norm from before decays like n to the minus 1 over d. Yeah, which is in contrast to the stronger condition that the covering radius decays like n to the minus 1 over d. Yeah, and time short, so just a very short note. This is also known in quantization theory as the distortion of the point set, in case you want to conduct some research. Okay, 2 examples in the end. The first example is if we have data points with one big hole. So if you maybe have good data, but you lost some data in a certain area or something, then we can examine how good this data is. So what do we have? We have some point set in the domain omega, which actually has the optimal covering radius up to some ball Bn of radius Rn, where you don't have any information about the function. Now the question is, how large does this hole, is this hole allowed to be in order that you still have the optimal order of convergence for the point sets? And the answer is, you can easily compute that the hole is allowed to have a radius up to order n to the minus 1 over d plus 1 over gamma plus d. So you have this additional power, this polynomial rate n to the 1 over gamma plus d compared to the covering radius of the rest of the point set. So yeah, actually the largest hole may be in some cases much larger than the other holes if you and you can still achieve the optimal order of convergence. And now to the example from the beginning, to random point sets. So if we consider n independent and uniformly distributed points on the domain, then if we now want to study the quality of these random point sets for the function approximation problem, we only have to consider the distortion or the L gamma norm of the distance function. And this is actually already well studied. It's known that this L gamma norm of the distance function of, it should be a Pn here, of the random point set behaves like n to the -1/d. So optimally for all gamma less than infinity, and only for gamma equals infinity, we lose a logarithmic factor. Yeah, so I say in various ways. For example, if I take the expectation here, then I have this behavior. But also, for example, for the first case, you have, if you put n to the 1/d to the other side, you have almost sure convergence to some constants. So there are much stronger results. And maybe short, what's the intuition behind that? Well, maybe you know the Coupon collectors problem. So if you divide the domain into equal parts of area 1/n and let's say 1/k, and you now throw in maybe 10k random points, then you can be sure that you hit most of these boxes which you divided your domain into. Yeah. But if you really want to be sure that you hit all of these boxes, then you have to take k times log k many trials. And this is why we have this different behavior for gamma equal to infinity. Yeah, and what does it mean for our problem? This means that random data is actually optimal for LQ approximation or integration on the Sobolev space if and only if Q is smaller than P. So for example, it's optimal for the integration problem, this random data, for all, as long as P is larger than 1. Okay, I guess time's over. Here are open questions which you can look up if you want afterwards. Maybe let's stop here. The paper is almost finished. I hope you will be able to find it on the archive really soon, and maybe in the upcoming weeks. Thank you.
All right, yeah, let's thank the speaker. Are there any questions for the speaker?
Yeah, I have a quick question.
Yes.
So David, do you think that there is a chance that this distortion function can give you some upper bounds for discrepancy? Or maybe I missed something. Maybe you already said that. I'm sorry.
No, I didn't say that. And I think the chance is not really good because
Okay.
somehow we only consider like, well, for discrepancy, it's empty boxes or boxes in general. And here we only consider cubes. And I think it's much of a difference if you consider rectangles compared to cubes.
Right, yeah. Is there a chance that maybe something for the isotropic discrepancy or something like that?
You mean where you only consider
convex, or for some sort of discrepancy? Yeah, maybe not necessarily the star discrepancy. But
well, I think you can get something from it, but it will be I'm pretty sure that it will be suboptimal.
Okay. Okay, thanks. Yeah, but this yeah, it's very interesting. Yeah, thanks. Thank you.
Thanks.
Maybe one question from my side to the one of Dima isn't this the same worst case error? Like I also only know it for the cube case. You take a Sobolev space of smoothness 1, and that's the same like discrepancy or something. Isn't that the same relation also there?
Right. Yes. For smoothness 1, the integration error is essentially the discrepancy. Although that's the integration error with equal weights, you're not optimizing. But I think actually if you optimize with weights, you still get discrepancy. Right. So the Cox-McLaughlin inequality with smoothness 1 will just give you.
Yeah, but for the isotropic spaces, you need something that grows with D, right?
Right.
Isn't it that you need something like smoothness D half or something like that? So can't you, so David, can't you transfer your integration result just to a discrepancy result by choosing the correct S?
So yeah, that's my question. Yeah, that's I don't remember exactly what the ranges were. So yeah, but it may make sense to look into it.
Yeah, but then of course you also have this the integration thingy. Here you allow arbitrary weights AI, where the discrepancy is more like weights 1/n. So for example, for random points, you have a much worse rate for if you only allow weights 1/n, because then it's bad if you have 2 points close to each other or a clustering of points. While for us, this doesn't matter. If we have a clustering of points, we just take small weights for these points, and then everything's fine again.
Other questions?
Sort of on the same domain, I find it interesting that the data we're comparing against, this distance function, is symmetric, but the weights on the optimal algorithm do not need to be symmetric, and if I understand you correctly, shouldn't be symmetric if the points are too close together. So is it sort of saying that if your point set is not particularly well distributed or what have you, then that the optimal algorithm can be weighted in such a strange way as to make it, well, as optimal as you can get given the distance function constraint. Is that what we're saying?
Yes, if I understand you correctly, that's basically what we're saying. Actually, in the proof, in the case without the boundary condition, maybe where's the picture, we actually do a step where we simply throw away all the points which are too close to each other.
Right.
And we throw them away. For the integration problem, this would just mean setting the weights to 0.
I had a question. Just when you were talking about the fooling function, it made me curious. Right, that whole idea that you were saying that, right, you can multiply by -1 and it doesn't really matter. It just made me wonder about, is there any worker? Do you know if there's any worker interest in any of the things we saw here in like a complex setting? It just, when you were talking about the fooling function, how you can multiply by -1, that just made me think of, well, maybe, you know, anything that's on the unit circle in the complex plane. And so I was just curious.
Yes, you can do the same there actually. And actually the only important thing is that this class of functions, so in this case it would be the unit ball, but you can also consider other classes of functions, that this is convex and symmetric. Yeah, we use the convexity. Well, we use the symmetry here. We take -f star, but we could also take I times f star, I guess. And we use the convexity here when we take for the upper bound. So I think you can do everything the same way if you just have a function class which is convex and symmetric, and then it doesn't matter whether the functions are real valued or complex valued.
Thank you. Any other questions for our speaker? Well, just in case, I'll stop the recording now.